The work of Nobel Prize has transformed our understanding of the world. While approaching the Nobel Prize winners in chemistry, we not only learn their achievements, but also the spirit of honesty, tenacity, innovation, and forging ahead.
Hi everyone, welcome to today's class, Approaching Nobel Prize Winner in Chemistry. 同学们大家好，欢迎走进今天的课堂，走进诺贝尔化学奖。Today I will introduce you a famous scientist. His name is Martin Karplus for computational chemistry. When you recall your chemistry class, teachers often use something like the sticks and balls to show you the structure of a chemical. But nowadays, we more like to use computers to display the models. In addition, the understanding of detailed chemical process enabled chemists to reveal the mysterious world of chemistry. But because the chemical reactions are so rapid that electrons move rapidly between nuclei, traditional experimental process cannot snapshot every single reaction step that happens so fast. So we need to reveal that mysterious world of chemistry with the help of computers. Martin Karplus, Michael Levitt, and Ira Warshall was awarded jointly for the development of multi-scale models for complex chemical systems for the Nobel Prize in Chemistry in 2013.
Paraphrasing Ralph Waldo Emerson, I shall try to show in this lecture how I've gone where there was no path and left a trail. Now, in trying to apply computational methods to complex systems, the essential idea has been to introduce classical concepts wherever possible to replace the much more complex quantum mechanics. And if we look at something that Dirac wrote in 1929, which many of you are familiar with, he said, the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known, and the difficulty is only that the exact application of these laws leads to equations that are much too complicated to be soluble. Many people know this, but they may not be as familiar that this was only the first part of a paragraph which went on.
Their work helps us improve the processes of catalysis, drugs, even solar panels. Now chemists all over the world design experiments on computers every day. The world around us is made of atoms that are joined together to form molecules. During chemical reactions, atoms change places and new molecules are formed. To accurately predict the course of reactions at the sites where the reaction occurs, advanced calculations based on quantum mechanics are required. For other parts of the molecules, it's possible to use the less complicated calculations of classical mechanics. In the 1970s, Martin Karplus and the other two scientists successfully developed the methods that combines quantum and classical mechanics to calculate the courses of chemical reactions using computers. The research of Professor Martin Karplus and his group is directly towards the understanding of the electronic structure, geometry, and dynamics of chemical and biological molecules. In each study, a problem that needs to be solved is isolated, and the methods required are developed and applied. In recent years, techniques of initial and semi-empirical quantum mechanics, the theoretical and computational statistical mechanics, classic and quantum dynamics, and other approaches, including NMR spectroscopy, have been used. How to develop multi-scale models for complex chemical systems from simple modes such as a hydrogen atom plus a hydrogen molecule to biomolecules. In developing computational methods to study complex chemical systems, the essential element has been to introduce classical concepts, whether or not possible, to replace the much more time-consuming quantum mechanical calculations. In 1929, Paul Dirac, the Nobel Prize winner in physics in 1933, wrote the following statement. The underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known. And the difficulty is only that the exact application of this law leads to the equations that are much too complicated to be solvable. It therefore becomes desirable that approximate practical methods of applying quantum mechanics should be developed, which can lead to explanation of the main features of complex atomic systems without too much computation. To understand the behavior of complex systems need, first of all, the potential surface on which the atom moves. Secondly, the laws of motion for the atoms. The most important approaches for representing the potential surface of complex systems which do not use quantum mechanics, the so-called force field, was developed. To study chemical reactions, the classical force fields were extended to treat part of the system by quantum mechanics, the so-called QM and MM methods. Although the laws governing the motion of atoms are quantum mechanical, the essential realization that made possible the treatment of dynamics of complex systems was classical mechanics. Such description of the atomic motion is adequate in most cases. This realization was derived from the simulation of the hydrogen atom plus hydrogen molecule exchange reaction. This video shows a non-collinear reactive collision. In this diagram, it shows the atom distances during reactive collision. The yellow box indicates that the strong interaction region. And this radio shows a non-collinear, non-reactive collision. In this diagram shows the atom distances during non-reactive collision. The yellow box indicates the strong interaction region. Classical mechanical dynamics based on generalization of the hydrogen plus hydrogen 2 methodology was applied to a large number of atoms. Obviously, the best way to elucidate the motion would have been a film of the trajectory. However, the computer graphic facilities available to us were not advanced enough to treat a 458 pseudo-atom system in infinity time. Instead, Bruce Galli made two drawings of the structure BPTI as shown in this figure here. One at the beginning of the simulation as shown at the left, and the other one shown at the right after 3.2 picoseconds. If you look carefully at the figure, you can see that although the two structures are very similar, every residue has moved by a small amount. Given that computer graphic can now make the desired film or the trajectory very easily. Viktor Ochamakov produced a film for the Nobel lecture using the corresponding representation. These quotations raise the question, how nature through evolution has developed the structures of proteins so that their jiggling and wiggling have a functional role. As the figure 20 shows, there are two aspects to this. First, evolution determines the protein structure, which in many cases that is made of relatively grid units that are connected by hinges. They allow the units to move with respect to another. Second, there's a signal, usually the binding of a ligand, that changes the equilibrium between two structures with the grid units in different positions. As an example, adenylate kinase, an enzyme, had two major conformations shown in this picture. On the left of the figure is shown the open structure, which permits the substrate to come in and the product to go out. And on the right is shown the closed structure. The closed structure creates a reaction chamber, which is isolated from the solvent and has to catalyze residues in position for the reaction to take place. As we can see, the top of figure 22 shows a series of snapshots from a cartoon movie with the substrate coming in and the enzyme closing. And the bottom of the figure shows the reaction taking place and the enzyme opening up to allow the products to escape. How about the feature of computational chemistry? Experimentalists use simulations as a tool like another. Applications of simulations to ever more complex systems, always with cautions that simulations like experiments have their limitations, inherent errors. Today's class tells us with the development of computers, how does it help us to predict and mimic the chemistry experiments? We have to thank Karplus. Thank you for watching.
大家好，卡普拉斯的得奖对我们有什么启示？第一，敢于想象，不怕风险。用70年代的笨拙计算机来做小分子量子化学计算已经很不容易，但它就已经开始计算蛋白质大分子了。更不用说，它居然把量子化学和分子动力学结合起来计算大分子，而不管当时的计算机只能模拟几个皮秒的运动，做费时大计算量的工作，几个月甚至几年的反复计算才会有结果。但结果如果不符合实验，就等于白做了。不怕风险，虽然这不是成功的保证，但只有这样才有真正成功的可能。第二，不要怕烦。学物理出身的人往往想把问题简化，但对于生物现象，关键之处经常在于细节，简化马虎不得。一个分子动力学程序里用到的蛋白质能量函数有上千个参数。卡普拉斯的得奖是对全世界做计算生物学的一个鼓励。计算生物学，特别是分子动力学，不像量子化学，还不是一个被普遍认可的学科。这主要是由于它往往用于解释已知现象，而不是一个很好的预测工具。也许只有等有了远超于现在的计算机，一切从量子力学开始，生物高分子的全部秘密才能向我们展开。在这样的超级计算机来到之前，大部分的生物高分子的研究只好靠对已知数据的挖掘来完成。这就是生物信息学，一门方兴带爱的学科。好了，本次课到此结束，谢谢大家，再见。